Welcome, everyone. Welcome to the 69th Annual Gilbert Newton Lewis Memorial Lecture. As many of you know, this prestigious lectureship was established in 1954 through an endowment from Dr. George A. Linhart in memory of his teacher, G.N. Lewis, and is held annually in October to commemorate Lewis's birthday, which is October 23rd, 1875. Now, as many of you also know, Lewis served as Dean of the College of Chemistry for a remarkable 29 years, during which time he recruited faculty by the name of Latimer, Hildebrand, Pitzer, Joke, Calvin, and Seaborg, to name but a few. For those of you counting, that list includes 3 Nobel laureates. In fact, Lewis's 50-year career spanned what is widely regarded as one of the most brilliant periods in scientific discovery, made even more so by his own contributions, which include his octet theory and electron pair bonding diagrams, not to mention the generalized theory of acids and bases, which bears his name. So how do you adequately commemorate a name like Lewis? Well, the answer is with Lewis lecturers like Jeff Reimer, a professor of the graduate school here at Berkeley and our speaker today. A Renaissance polymath in his own right, Jeff and his group have been generating new knowledge for environmental protection and sustainability and providing fundamental insights to condensed matter through materials chemistry, physics, and engineering for the last 40 years here at Berkeley. As an undergraduate, Jeff studied chemistry, physics, and biochemistry. I guess he couldn't make up his mind, and ultimately received his bachelor's degree in chemistry with honors from UC Santa Barbara in 1976. Jeff was the first in his family to get a college degree. Jeff ventured on to Caltech for his graduate studies, which, by the way, is where I first met him. But during his 3rd year as a PhD student, his thesis advisor, Robert Vaughn, tragically died in a plane crash. So Jeff cold called Xerox PARC and persuaded the physicists there to take him in and host him for the last year of his PhD. While his chemistry PhD peers sought jobs as postdocs in academia, Jeff went on to IBM in Yorktown Heights and split his time between silane reaction engineering in one division and semiconductor physics in another. Upon leaving IBM, Jeff received faculty offers in 3 different disciplines: chemistry, physics, and chemical engineering. Luckily for us, he chose chemical engineering here at Berkeley, and he began his independent career as an assistant professor in 1982. For his many notable research achievements, Jeff has been honored as a fellow of the American Association for the Advancement of Science, the American Physical Society in the Division of Materials Physics, and the International Society for Magnetic Resonance. He also received a Humboldt Research Award in 2014 for his work in materials chemistry and physics, along with many other accolades. Equally impressive is Jeff's impact on the Berkeley science community in regard to classroom teaching. And I'm not talking just about the hammer pants that Jeff is famous for wearing to lectures. Now, for those of you who aren't familiar with hammer pants, I encourage you to Google it. Jeff is the recipient of a Camille and Henry Dreyfuss Teacher Scholar Award, the AICHE Northern California Section Award for Chemical Engineering Excellence in Academic Teaching, the Donald Sterling Noyce Prize for Excellence in Undergraduate Teaching, the CBE Department Teaching Award, both in 2000 and in 2015, and the UC Berkeley Distinguished Teaching Award in 2003, which is the highest campus-wide award bestowed on faculty for their excellence in teaching. He also initiated and co-designed 3 new courses in CBE: Applied Spectroscopy, Carbon Capture and Sequestration, and Introduction to Chemical Engineering Design. And he has co-authored textbooks for all 3 courses, which reach and engage a broad range of audiences. As if that's not enough, Jeff served as chair of the Department of Chemical and Biomolecular Engineering from 2006 to 2011, and again from 2013 to his retirement in June 2022. And that gives Jeff the distinction of having the longest tenure of any chair in the history of the ChemE CBE department at Berkeley, just as Louis has that distinction as dean. So what more could we possibly ask of Jeff other than to take time out from the first few months of his retirement to deliver yet another lecture? But this isn't just another lecture. This is the Louis lecture. And fortunately, when we asked Jeff, he agreed. So now let me turn things over to Jeff for his talk entitled, When the Chemical Bond is Not Enough. Please welcome Jeff West.
I'd like to think about this lecture as a novel. And the novel, of course, has a plot. The novel is largely autobiographical and largely chronological, covering really the last 10 years of work that my group and I have conducted in the area of carbon capture. But it's a funny kind of novel because it has a book jacket on either side. And the book jacket may seem a little odd to you, and I'm hoping by the end of the lecture you'll understand the images that I've used as the book jacket and why they pertain to the question of, is the chemical bond enough? So let's start with the first book jacket, the front cover, shall we? And let's go take a look at a famous spot on the way to the Strata, which is the building formerly known as Kroeber Hall. And what is it about Kroeber Hall that strikes you? Well, it's named after Alfred Kroeber, a famous anthropologist from the early part of the 20th century. Shown here in this picture is Alfred with one of his cultural studies, a man he gave the name Ishi, Native American. And in 1925, Alfred Kroeber, based upon his cultural and intellectual analysis, declared the Miwokma Ohlone Indian tribe extinct, which is to say, think about it this way. The years of colonialism, the years of the church, the years of the political and military power of the governments of the United States, the local governments, and finally the intellectual and cultural power of UC Berkeley have extinguished these people from the planet and separated them from their land. How fascinating it was then, a few months ago, when I saw this article in the New York Times, based upon a paper that had just been published in PNAS. And in this particular paper, genetic scientists and Native Americans got together and collaboratively worked on exhuming the bodies of Native Americans, some 2,000 years old, with the following question. Are they in fact related to the people who today claim themselves to be Miwokma Ohlone tribes members? And the answer was yes. In fact, the genetic analysis shows that these people who have lived an oral history of being a member of this tribe and yet separated from their land by the powers that be were suddenly realized to be, in fact, genetic descendants of the Miwokma Ohlone original peoples. So how fascinating it is, isn't it, that modern-day science would provide this connection to the oral history of Native Americans. And the question we have to ask is, the principalities and powers that exist today, what are they going to do with this new information? And that question is going to come up again at the end of the talk, so please don't yet go away. So let's turn to the body of the novel for a moment, and I want to talk about carbon capture. I have 3 slides that I use in public lectures about carbon capture because I have found them to be really compelling to the public audience. This one is particularly handy. It shows the concentration of CO2 in the atmosphere as a function of time back from today. And you can see the ups and downs that are associated with ice ages. Here we have an ice age here and one here. By the way, the year 200,000 BC is roughly when Homo sapiens were thought to emerge on the planet, although our greater ancestors went much farther back. But I'd like to show this to the public for 2 reasons. First of all, these are data. They are taken from ice bubbles trapped in, from air bubbles trapped in ice cores. And so the public can relate to physical measurements which tell us about the composition of the atmosphere, and not measurements that are inferred upon inferred upon inferred, although we as scientists are very comfortable with those, but I found the public generally not. The other thing the public can see is, look, here's the difference between an ice age and a warmer age, and they recognize quite readily that where we are today is a great deal different than any of those warming and cooling periods. So the public appreciates that we are in some sort of weird place with regard to the composition of our atmosphere. Another image I like to use, which is a reminder of, and where did that carbon dioxide come from? So let's take the year 2017. In that year, 1,400 million tons of carbon were introduced into the atmosphere just from coal-fired power plants. That same year, we produced 344 million tons of plastics, which is to say that coal-fired power plants put 4 times as much carbon into the air as all the plastics manufactured on the planet that year. And that's something the public can grasp. And the last image I like to use in public lectures, which is thanks to Arun Majumdar, our colleague at Stanford. He likes to point out, and I love this image very much, that if you add up the mass of the people on the planet, that turns out to be about 0.5 gigaton. That's a lot. I know I contribute too much myself. In 2021, humans emitted 34 gigatons of carbon into the atmosphere, which is to say we put 60 times more carbon into the atmosphere as the mass of all the people on the planet. So people get this, and they understand that we've changed the atmospheres. Now, you could take our whole course on carbon capture and learn about all the consequences, which I won't go through. Let's turn now to the plot of the novel, as it were. So we are interested in looking at sources, such as industrial gases, which typically range from 5 to 50% CO2, and subjecting those gases to some sort of unit or chemical process. I've listed 4 here: bubbling gas through a fluid, blowing gas over a powder, pushing gas through membranes, reacting gases with strong bases. And I show those not because they're the only options, or for that matter, maybe they're not even the best ones, time will tell, but they're options that are readily scalable to the kinds of tons, gigatons, that we need to address on our planet. The presumption, of course, is that we can do something with that CO2 once it's captured, either sequestered in underground or other kinds of storage, or, as some clever chemists are imagining, taking CO2 from the atmosphere and converting it into a fuel or a product that would recycle carbon in a circular fashion. But if you ask the IPCC what's needed, they will tell you that we also need to do direct air capture, which is to say, all the mitigation that intercedes in our industrial processes is not enough if we are to keep to the 2°C protocol, and that's a worst-case scenario in some minds anyway, then we have to do some sort of direct air capture. And these processes wind up capable of doing the same thing. So the Berkeley work I'm going to talk about today is really about capturing these gases in these kinds of situations, and I'm going to talk about using powders or adsorptions for reasons that I think will become clear near the end of my lecture. So, what's the first class of materials that comes to mind when you want to capture anything from a gas? Answer Jeff Long says, MOFs, okay? So the answer is metal organic frameworks. These are an interesting chemical platform. Why? Because they're exquisitely tunable and assemble in such beautiful and elegant ways so that we can test a lot of hypotheses about how CO2 might react in transport. This particular MOF is called MOF5. It's built around a linker, this terphthalic acid, and the zinc oxide tetrahedra. It's, I think, one of the first MOFs invented. It's largely attributed to our colleague Omar Yaghi. And it was Omar who came to Jeff Long and myself and others in about 2012 and asked the following question. What is the nature of the distribution of bonds in this system, particularly if I construct it from linkers that have different compositions? So you notice all these molecules look sort of the same, don't they? Except they have slightly different pendant groups that might result in different kinds of chemistry. And the question Omar was asking, let's label those molecules with colors. If I dress a MOF5 with linkers of varying colors, does it matter? In fact, the more important question at the time was, if that's what the linker distribution in space looks like, how do you measure it? See, it's not a regular periodic array, so you're not going to be able to do scattering. And the length scales of these linker distances are too short for microscopy. So we need some other strategy to discern that. And for that matter, does it even matter whether the distribution of colored balls is random or not? Well, the first question we can answer right away, and we do that with computers. And so the idea is you take one of these metal organic frameworks, like this one, which has 3 different kinds of linkers, and you build it into a computer, and you conduct molecular simulations for the absorptions of CO2. And with apologies to my simulation colleagues, roughly this looks like you build the lattice on the computer, you insert a CO2 molecule, you calculate the energy, insert it again and again and again, and you do that a few million times. And from that, you derive a force field. And from that force field, you can calculate the absorption coefficient of CO2 in these systems. And so here you see that in this this triply labeled linker, MOF, if you have alternating linkers or clustered linkers, you get a very different amount of CO2 uptake versus pressure. So this is important because the capacity of the material to absorb CO2 tells us how effective it's going to be in a device. The size of the box that's going to purify our air depends on this capacity. So if I can tune it by adjusting the apportionment of linkers, then I have a handhold on making these materials more efficacious. So here's what a distribution might look like for a binary system, of course blue and gold, right? In which case I have large clusters, small clusters, random and alternating. These are the kinds of apportionments one might expect. And if I were teaching a class, you'd pull out a piece of paper right now, and I would ask you the following question. In which of these apportionments is the average distance between a blue and yellow ball largest? And if I could measure the average distance between a blue and yellow ball, would that tell me the apportionment? And hopefully you'll realize quickly that in this structure here, where the blue and gold are next to each other, this is the shortage average distance, and this would be the longest. So if I can measure the distance between the balls, I might have a handle on discerning apportionment. And this is where I join, or my team joins this particular question, which is how to measure average distances. So with the help of Omar's team, we are synthesizing linkers in which we put spin labels, for example, on a methyl group or on an NO2 group here, and we're going to use the dipole-dipole interaction between these 2 spins as a way to determine their distance. And the way this is done, and I know many of you are not NMR people, but I'll just mention that NMR is a very funny space to work in as a quantum mechanic. And the reason it's a funny space is because spins are so isolated from one another and isolated from the environment, you can actually write Hamiltonians down analytically. And you can subject those Hamiltonians to all kinds of time-dependent processes and govern the spin dynamics of the system in a very straightforward way. In this particular case, I'm going to excite the carbon-13s, and I'm going to allow the equations of motion to evolve for a period of time, and then I'm going to invert the sign of time in the equations, which you can do. And then at the end of that, I'm going to recover the signal that I started with. And in every other experiment, I'm going to introduce an interruption. I'm going to provide pulses to the nitrogen nuclei, and these pulses interrupt my ability to refocus this particular Hamiltonian, and the net result is a smaller signal. The ratio of those signals as a function of the recoupling time, this time here, gives me what's called a Redor curve, very famous curve in the NMR world. You're really clever at the cocktail party. Talking to an NMR person, you can talk about Redor. That puts you in the inset right away. The nice thing about Redor is that because you're dealing with a pairwise dipole-dipole interaction, that's a cylindrical interaction, so that interaction is described by Bessel functions. And so there's an analytical solution to these Redor curves. The argument of the Bessel function contains the distance, and boom, I've got the distances measured. Omar synthesizes a gaggle of these MOFs. We run these experiments, and 2 years goes by. And the reason 2 years goes by is it's not completely obvious, with the exception of the extremes, when the balls are all isolated or the balls are next to each other. It's not completely obvious how to connect the average distance to the spatial distribution. And towards that, we have to turn, once again, to molecular simulation. So what we're going to do is build a lattice on a computer. I'm sorry I don't have blue and gold balls now. They're green and orange. And we're going to put them on the computer, and we're going to introduce a pairwise interaction between green and green balls, between orange and orange balls, and between green and orange balls. And we're going to subject those balls to a Monte Carlo simulation. That is, we'll randomly move them around, calculate the energy, keep doing that a few tens of millions of times until the energy is constant. And then we'll reconstruct the atomic structure, calculate the Redor curve from that structure in the computer, and compare it to the data. Bad fit. Okay? So we'll adjust these pairwise interaction parameters and keep doing it until we get some sort of least squares best fit. That's another million or two operations on the computer. But in the end, the best fit can be projected and will look like the kind of pictures that we were accustomed to seeing. So what do the data look like? Okay, here's linker F, a methyl group, and linker B, an amine group, N15, carbon-13, and this one winds up exhibiting small clusters. In the case where the other linker is an NO2 group, this winds up looking random. If one of the linkers has very large arms and hands, so that it's very large, then of course what happens is it becomes alternating. As you can imagine, next-door neighbors of the same girth don't fit together very well. We can do this for trinary systems, that is, linker E, linker H, measure EH distance, EI distance, run it through our simulations, and we see this one is alternating. So now we have a mechanism to connect the average distance to the apportionment, and is it right? So the answer is we're going to go back and look at these data again. So remember that the molecular simulator said, here was large clusters, here was alternating for the adsorption capacity as a function of pressure. In this particular system, NMR says it's alternating, and we go to the laboratory and measure the data and see that it's consistent with the alternating structure. So I'm very pleased to report that this worked. It worked reasonably well, and other groups around the country are now routinely employing these distance measurements to get the apportionment of linkers in metal organic frameworks. And I just want to point out that the NMR work in this project was led by my former postdoc Sean Kong, who's now a professor at Zhejiang University in China. So if apportionment works for the linkers in my giant molecular tinker toys, does it work for the metals? That is to say, if I imagine now not exchanging linkers but exchanging metals, whether they're clustered or whether they're randomly distributed, does it matter? And the answer is, I don't know. But there's a context in which we can test this question. And the context is, if you look at the production of hydrogen, the production of biogas purification, that is, vegetable matter turned into gases, natural gas purification, you wind up with a mixture of these kind of gases. And obviously, if you're making H2, you don't want the others, and so forth. And it turns out that magnesium MOF74, another MOF, is very facile at capturing CO2, and the nickel MOF is very facile at capturing CO. And we wanted to know the following question. If I mix these metals up, does it matter how they're apportioned? And does it matter how it executes the kind of separation between carbon monoxide and carbon dioxide? Which is to say, is it the chemical bond or the distribution of bonds in space that matters? So how do you discern the apportionment of metals in a molecular material? Well, the first thing you could imagine is, well, how do I just figure out how much is there? And the tools of analytical chemistry work very well for determining you have this much magnesium and this much nickel. You can imagine going to a microscope, focusing the beam of the microscope down to a very small dot, and using X-ray dispersion to get the magnesium to nickel ratio. You can do that too. Unfortunately, the length and volume scale of that analysis isn't anywhere near that of the distance between the balls in my tinker toys. Omar courageously published a couple of years ago this experiment in which you took a rod of a MOF, ablated one end of it with a high-power laser, and then used acceleration on a position-sensitive grid to detect the presence of metal ions. Extremely courageous. Thank you, Omar. Alas, it's destructive and maybe not universally applicable, and so we decided to come at this again from the point of view of magnetic resonance. And so let's take a look now. I'm going to build MOF74, which is different than MOF5. It's made of a different kind of linker. It's not terphthalic acid, but you'll notice it has these hydroxyl groups on it. But I'm going to enrich these carbons with carbon-13. And so when I build the MOF and do carbon-13 NMR, I see only one peak. There it is, right there. The chemical shift is exactly what I'd expect for that kind of molecular moiety. All is good. Let's put a little bit of nickel in. And notice what has happened. There's a whole lot of peaks appear at very unusual chemical shifts, and even around the original chemical shift, there's a bunch of different peaks. So what is going on, and how is that useful in discerning apportionment? And this is where, this is a story in magnetic resonance, goes back some 60 years, which I won't dwell on you. But what I will say is, if I'm a carbon here, I'm bonded to an oxygen, and that oxygen is bonded to a metal that has unpaired electrons. Those electrons exert a torque through the bonds onto the nuclear spin. And you're used to that already. All of you know about J-coupling. You use it every day when you do your synthetic chemistry studies. But in this case, you don't get a splitting, you get a shift. And the reason is because the electron spins are relaxing so fast, it's only a net magnetic moment. So it's like a bar magnet, a few bonds away, exerting this torque. And that's why you get these peaks. And we can use the techniques of NMR spectroscopy to unravel all the artifacts that are present in this spectrum from the real data. I won't dwell on the details, but we can fit all these peaks analytically and extract the numbers we need. And so now, what is now the physical meaning of all these peaks? And as our friend Arup Chakraborty once said to me, when luck knocks on the door, don't slam it in luck's face, right? And the answer is because if you just look at, here's the two carboxylate oxygens here, and here's the three metal bonds in the MOF. And if you take two different metals and distribute it amongst three sites, there's 8 ways to arrange those. So for example, all nickel, all magnesium, a nickel here, and so forth and so on. And guess what? There are 8 peaks. So yes, indeed, that seems very fortuitous indeed. And so now we have to subject this to a further analysis. So here's what we do. Many of you are aware of a Karplus curve, I assume, which is to say you know how to predict J-couplings in CH bonds, for example, as a function of dihedral angles, from Martin Karplus. Well, Claire Gray at Cambridge came up with a way to propose similar empirical rules for this through-bond interaction from unpaired electrons. And in so doing, we're able to tentatively assign these peaks by looking at these empirical rules, that is, bond distances and bond angles. And so we think we know what each one of these peaks are, and we're ready to publish? Not quite. Not quite sure I completely trust those. So let's take a look at some DFT calculations. That is to say, I'll use the tools of molecular quantum mechanics to try and calculate these shifts. Turns out, Martin, I don't think he's here. Regrettably, Martin, you can't do this well yet. But on the other hand, what we can do with these kind of shifts is get their order. That is, the farthest shift and the closest shift to the diamagnetic species. We can get that order correctly. And then we can also look at the magnetic susceptibility of these materials at low temperature. And they all consistently allow us to do the assignment. This peak is for this one for this one, and so forth and so on. Whew. Okay, so now we've unraveled all 8 peaks. Now what? Well, let's now take a look at CO2-CO separations in one of these MOFs and then look at the capacity for CO2 as a function of the nickel content. And what you see is really nothing very interesting at all. That is to say, it's linear. The highest nickel is the worst CO2 adsorber, and so forth. No surprise. A bit of a surprise, though, was carbon monoxide. And you see that unlike the linear trend, it shows this very nonlinear trend with peaks up at around 40% nickel. And if I look at the coverage of carbon monoxide as a function of the nickel content, I see that it maximizes right about 39%, which is to say this magical formula, which is predominantly bond in this kind of arrangement, 2 nickels and 1 magnesium, is optimal for absorbing CO from these mixtures. So again, we'll turn to density functional theory, and again, we'll calculate what's going on here. And for the pure nickel system, we recognize that carbon monoxide bonds terminally, but for the system in which there are 2 nickels and a magnesium nearby, there's the opportunity for bridge bonding of carbon monoxide, which is to say a new bonding mode opens up in the presence of this local apportionment of metals that isn't present in the other apportionment. So in this context, then, this one is a particularly effective separating agent because of apportionment. So indeed, it does matter for metals, and it can be measured, and NMR is the tool to do that. And I just will add, this will come out next week in Science Advances, and the main author who did all the NMR work is Jun Xu, my former postdoc. Okay, so where are we at now? I've been trying to argue that an individual chemical bond, as G.N. Lewis so wonderfully articulated to us, is insufficient to account for carbon dioxide capture in materials where these bonds intermingle with one another in some sort of precise way. That leads us to the following question. Can I do the inverse? Can I imagine on a computer a construct in space that has particular spatial locations of atoms that's optimal for separating CO2 from, say, a coal-fired power plant? Actually, no surprise to the biologists or biochemists in the room that mainly the three-dimensional structure of many atoms in one place has import in biochemistry. And of course it does in the pharmaceutical industry, where pharmaceutical scientists will know a target molecule, a protein, for example, in your body. And what they're interested in is a small molecule that will bind to that protein to produce some sort of medical effect. And the pharmacologists will use computer screening to look at millions of small molecules to find ones that are right shape, right size, right energetics to bind with that. And they call these small molecules pharmacophores. Our problem is the inverse. We know exactly what the small molecule is. It's carbon dioxide. What we don't know is the adsorbophore. That is to say, the three-dimensional structure in space that takes up CO2 and excludes water and nitrogen, which is what these separation processes have to do. So how are we going to do this? Again, we'll start with the computer. We'll go to a database like the Cambridge database, and we'll look at many, many structures that are in that database. Let's take about 350,000 or so of them. We've looked at a lot more since this was published, but we'll start with those. And we'll use those same computer methods to calculate the adsorption of CO2 versus, for example, nitrogen. And we'll take a look, and here's where we have the working capacity for CO2. Remember, a high number is good. And a selection against nitrogen, a high number is also good. And we look at this and we say, aha, we'll take these 8,000 or so that look pretty promising. And we'll go back into the computer and ask, what does the active site look like that binds that CO2? And we'll use graph theory to sort of bin those structures into various types. And what are the types and what do they do? Well, so what we'll do is we'll take these adsorbophore types and examine their sensitivity to water. Here's the affinity for water on this axis and the affinity for CO2 on this axis. We want low affinity for water, keep water out. We want high affinity for CO2. And these are the structural types. So for example, parallel aromatic rings. And the chemists in the audience will understand completely that two such rings is a very hydrophobic environment, and that excludes water. But it would certainly include CO2. So this seems like a promising case. Sorry, I hit the wrong button there. So here's what we have then. We have these candidates out here that look very promising. And we look at the database and we're going to select about 35 of them because they're similar in structure. They all possess parallel aromatic rings that are about 7 angstroms apart. Okay? So now we have a target. We have 35 or so MOFs that we should make. Are they made in the literature? Mostly not. So we have to resort to all kinds of techniques to make them. And this is where synthetic chemistry comes into play. Because not only do you need crafty, clever synthetic chemists who know how to make crystals of these MOFs, but in some cases you just have to use a robot because there are so many options and choices for how to do it. In any case, that's what we do. And we did wind up making a couple of them. And as you can see by this cartoon here, this is one of them, one of our favorites. Let's take a look at it. This is the structure of the MOF. You see these polyaromatic centerings based on the pyrene linkers, and they're 7 angstroms apart. The reason we like this is because the metal is aluminum, easy, cheap to get, lightweight, and the linker is already available in the pharmaceutical industry, so at least at first screening it passes our LCA test. So now what? The X-ray structure looks exactly like we think it should. And so the real question now is, remember that all this was predicated on computer simulations. Did the data match the computer simulation? And the answer is pretty well. As an experimentalist, when I look at something like this, I think, oh my God, you're a failure. But I'm told by simulation people, this is a grand success. And so I'll take their word for it. But especially at lower pressures, you can see the consistency between theory or simulation and experiment is very high. So the whole metric upon which the screening process was predicated seems to hold up. All right, so what do we do now? We go to engineers. We pack a pipe with powder. We introduce, let's say, the exhaust gas from a coal-fired power plant or a proxy thereof. We push it through the pipe. We generate what's called a breakthrough curve. Here's the amount of CO2 capacity in the material as a function of time. And we just notice, for your purpose, that wet and dry are very similar, which is to say the notion of excluding water so that CO2 can be captured seems to hold true. We can cycle the material. Here's the working capacity as a function of the number of times we absorb CO2, either heat it up or drop the pressure or both to take it off, put it on, take it off, take it on. So that 10 times. And our favorite here, Alpimov, cycles very, very well, at least up to 10 cycles. So that's a good sign. So we designed it on a computer that looks like we created something that works from an engineering point of view. The question is, does in fact water, is it excluded from this active site or not? And towards that, we're going to turn to spectroscopy, of course. And so what I'm going to do is look at the carbon-13 NMR spectrum of the carbon atoms that make up the linker, as shown here with these labels. And I'm going to look at the line width of those as a function of relative humidity. So when a water molecule is close to carbon atom A, it's going to broaden that line. And what I see is that up to 60%, none of the lines are broadened. And at 80%, just those carbons that are close to the oxygen start to see any water. That's a good sign, at least qualitatively suggests that water is not anywhere near the active site. If I now just look at carbon-13 NMR of C13 labeled CO2, and I put that in, and do the same experiment, and what I discover is there's almost no change in line width. So the good news is that it looks like it's doing what's told. The bad news is that the way in which I conducted this experiment really interferes with the broadening process, so it's only qualitative. Can we do better? Sure, the answer is we'll stop this rotor, we'll do static carbon-13 of C13 label, we'll look at it as a function of humidity, and there's no real substantive change in the spectrum with humidity, and even when we replace H2O with D2O, so the broadening mechanism go away, there's no change. So the absorber was designed de novo on a computer. It was assembled in space by synthetic chemistry. Engineers showed that it was a successful adsorbent, and spectroscopy showed that it works as designed. And I'll just say that the postdoc of mine that did our part of this effort was named Rich Bounds, and he's now a quantum mechanic in the UK. All right then, last topic, we're getting near the end, which is, didn't G.N. Lewis know about how to separate CO2 from gas streams? And the answer is, of course he did, because in those days, there was already a well-known chemistry. You take carbon dioxide, which is a weak acid, and you mix it with amines, weak bases, and you form ammonium carbamate Zwitter ions, and you heat these up, and they come back to where they were, which is to say a gas with many chemicals in it goes into a solution of amines. The CO2 is bound, the others pass through, you heat it up, and the CO2 comes off. Good as gold. That is to say, the chemical bond is enough, as G.N. Lewis would say. And indeed, you can go to a place in Texas, this is the Petronova plant, and they've captured over 1 million tons, as this caption says, of CO2, regrettably only to use that CO2 to get more oil out from underground. We'll hold our judgment on that for a moment, other than to recognize that this facility works at the kind of scale we need. The bad news, of course, is that you need about 1/3 of the power plant to run that thing, which is to say your electricity bill goes up by 1/3, or the power plant output goes down by 1/3. And that's only one of a long list of attributes that are negative about this process. So what are we going to do? Well, the answer is we want to make a porous material for which heating and cooling is relatively, quote-unquote, straightforward. And we want to imbibe this chemistry into this kind of material so as to conduct carbon capture. Now, the absolute reigning king of this concept is sitting right over there in that corner. That would be Jeff Long. And Jeff Long has imagined and executed placing amines inside of MOFs to do just this. I've been a little bit of a part of that work. Thank you, Jeff. It's been a real blessing to do that. I'm not going to talk about that today, but I do hope Jeff gets a chance to talk to you all about that sometime soon, because it's a really compelling and brilliant story. But we decided to look at this one other way, which was, could I do this on the cheap? MOFs, are expensive and delicate and interesting to make, but can I find things that I can just get really cheap? And can I do the kind of chemistry that we hope could happen? So here's what we're going to do. We're going to start with Formica. Yeah? Do you know what this is? Your picnic ware is probably made of Formica, maybe your countertops. This is melamine and formaldehyde with DMSO as a solvent, relatively modest conditions. You form an amorphous polymer, sometimes called Formica. Alas, it doesn't capture CO2. It's not porous enough. So my colleague said, okay, here's what we'll do. We'll add some cyanic acid to this and open up the polymer so that it has pore space. Cyanic acid, you may recall, is the thing you add to your swimming pool to stabilize the chlorine. So it too is cheap. Alas, this doesn't capture enough CO2 either, regrettably. But my group was even more clever. They said, let's take off of what Jeff Long has been doing, and let's just add the cheapest possible amine we can buy. This is $4,000 a megaton. Okay, so it's cheap, right? So we're just going to imbibe this polymer with this. And can it be done? Absolutely. An average student can make a half a kilogram in a day, no problem at all. So it's cheap and easy to make. The question is, does it do the kind of chemistry we hope? And is it really this kind of chemistry, or is it something more complicated? All right, then. So if you take a look at this material and ask, where does CO2 react? You suddenly realize what a vexing problem, what a puzzle this is to unravel. So first of all, we don't know whether CO2 reacts at one end of the triamine and then the other end, whether it attacks in the middle, that is the primary or secondary amines. We could guess, but we don't know ahead of time. We also don't know with these particular triamines whether we form ammonium carbamate, where the proton is on some other place somewhere else in the polymer, or whether we form carbamic acid in this structure right here. And not only that, we also don't know how these functional groups are distributed amongst each other. So for example, are these ammonium carbamate, are they paired up next to each other? Do the carbamic acids pair? Are there mixed pairs? So there's no fewer than 8 different equilibria that could be possible in this system. So unraveling it would seem to be problematic, but that's why we have such great students and postdocs at Berkeley as they tackle the impossible. Don't go away yet. I'm not going to go through this slide. I'm just going to tell you that a whole lot of experiments are involved here, particularly using a multi-dimensional NMR spectroscopy, building polymers with and without the cyanic acid, with and without the amines, and so forth and so on. But I just want to highlight quickly the use of multi-dimensional NMR in sleuthing out this kind of chemistry, because I think it's very clever and very important. In these experiments, you have a topographical map, not a graph of NMR spectra. So on this axis, this is the carbon-13 spectrum here. And if you project these peaks down here, you're going to see 2 bumps. And one bump is the carbon-13 shift for carbamates, and the other is for carbamic acid. On this axis over here, you're going to see the proton NMR spectrum. These are all solid state, by the way, where we use these methods in order to provide high resolution. And so these 2 carbon peaks would give rise at this chemical shift to interactions with the acid proton, with the ammonium ions, with the amide protons. And so it is this kind of strategy.
She wants to learn about law.
Hi. Sorry, I'm flustered now.
Worry about your next promotion.
Yeah. So Haiyan was able to use this sleuthing, like as shown here, looking at the connection between this carbon, this proton, and this proton, to unravel all this that's going on. And she was able to discern that ammonium carbamate pairs and carbamate-carbamic acid pairs are governing this particular system. And moreover, the kinetics of absorption, how fast CO2 is taken up, is good. The cycling stability is good. And so Haiyan Mao is the postdoc in my group who led all the NMR efforts on this with her friend and colleague Jing Tong from Yi Qi's group in Stanford, led this particular study. So I'm not done yet because we haven't gotten to the back book jacket. But I do want to thank the many people associated with the work in my lab. This is my current group right now at a picnic at our house. I could not go anywhere without mentioning Maddie. If you don't know who Maddie is, Maddie runs the entire world. There is no finer staff person on the Berkeley campus than Maddie Madison. And those of you who know her will know exactly what I mean. And my whole group is very grateful to her stewardship. I'm particularly grateful to the people who fund this work, and Department of Energy, NSF, a consortium of people in the European Union, and some foundations. All the works I've talked about have many, many fabulous co-authors who I have not named explicitly, and that's short shrifting them, and I apologize for that. And their work has contributed substantially to all of these. And of course, I have many wonderful current collaborators, including engineers like Alyssa, Barron, Susanna, and Yi. I have chemistry colleagues that I'm working with closely, and many thanks to Brett, Jeff, John, and Kyriakos. And some physical scientists, Ashok and Alex and Carlos, and I chose not to talk about the work we're doing together with them. We'll save that for another time. But all these people have enriched my life enormously, and I'm very grateful to them. Now, let's see. I said we were talking about a novel today, and I told you about the front jacket. Let me close with the back jacket of the novel, and that's going back to climate change. The most recent sea level rise report from the NOAA shows this kind of sea level rise by 2050. It's quite likely I'll live to 2050, although one never knows, but many of you will. And so we're looking at something like 1/3 of a meter of sea level rise, depending on the various strategies that we employ for carbon capture. And I'm sure all of you are aware of this paper that was just published 2 months ago, in which the authors looked at the current commitments for Greenland melting ice. And on top of this is another 274 centimeters, 0.274 meters, as shown by the arrow here. So we're looking at a pretty extreme situation between now and 2050 for sea level rise. Now, what does that mean exactly? Well, if you look around the planet at how oceans and currents occur, and you look over here, you recognize that in the western Pacific, southwestern Pacific, we have a great deal of warm water coming to the surface. Warm water expands with temperature more than other waters. And so if you lived here, you might be worried. And indeed, if you look at altimetry data from this paper in PNAS a couple of years ago, you recognize this is the average sea level rise according to satellite altimeters. And if you live here, climate change is no big deal for sea level rise, right? But of course, if you live here, you're in trouble. And we know this already because the Marshall Islands are disappearing. And if you live in Tuvalu, you recognize that your whole countries are going away. So now I'm going to close by bringing together the story of Alfred Kroeber and the story of climate change, which is that 100 years ago, the intellectual and cultural power of UC Berkeley and others extinguished a people and separated them from their land. Science may heal that with these genetic studies. Right now, we're separating people from our land, and it's possible that chemical bonds or the intermingling of chemical bonds will lead to the technological and scientific discoveries that mitigate this. But both of these problems have as their origin something different, something much bigger than the chemical bond, which is, what are we going to do about the powers and principalities that discern whose land survives and whose land doesn't? And until we address that, chemical bonds are not enough. Thank you so much.
Not only are you the longest running chair, I think that's the longest running ovation I've ever heard for a Lewis lecture.
Thank you all.
Before I call upon a very special guest whose arrival you've obviously already noticed, let's take a couple of questions for Jeff. David.
So Jeff, you
And
may be
then
the person who's uniquely qualified of anyone that I know to answer this question. Since you're trained as a chemist and you spent much of your career in the chemical engineering department.
Sorry.
How do we improve the education of both chemists and chemical engineers? Is there a way to do this so that chemists learn more about engineering, engineers learn more about chemistry?
I have a thought about that. You're not going to like it, but I'll say it anyway. So first of all, in my career, in my 40 years at Berkeley, here's what I've noticed. I've noticed that chemical engineering has gravitated a great deal to applied science. And I've noticed that chemistry has gravitated a great deal towards applied science. So I actually think there's evolution happening, not a revolution, but an evolution is happening where our disciplines are going to intermix. And the next big challenge, which Matt Francis and I talked about at one point in time, is when we start sharing courses. And I think that's the next big breakthrough when, for example, all first-year chemistry students, PhD, and first-year chemical engineering PhDs take a common course. I think that would be really exciting as a good first step. Brian, that's up to you now, and Matt. That's one possibility. The other thing I want to say, which is not pandering to our chancellor, trust me, but as you know, I have a long-standing feeling that liberal arts are short shrift in STEM education. And I think that one strong mechanism to bring us together is to have a bigger emphasis on liberal arts at the bachelor's level. And that means science and engineering students are going to have to set aside a little bit of something in order to engage in the liberal arts. And I know John has been talking about this for a long time. And I think that's another mechanism where we can sort of get together.
There was one in the back.
Oh, it's Jeff.
Yeah. Fantastic talk. It's been such a pleasure working with you in this area for many years now, and I hope that we go many more. So one question for you. Like you, I'm really interested in this nickel magnesium MOF with carbon monoxide.
Mm-hmm.
You show a structure with carbon on nickel and oxygen reaching out to magnesium. That seems a bit of a stretch to me. Those metals are 6.5 angstroms apart.
Sorry?
Do you think that's right? And should we do some diffraction experiments?
We should. And what I'll do, as a reminder of that question, since I don't have access to my computer, what I'll do is I'll come back to you and show you exactly the structure DFT shows as an energy minimum so you can comment on that, okay?
That'd be great.
Yes, I'd like that very much. That would make for a good day for me.
Bring more hands up out there. All right, well, let's thank Jeff one more time.
Thank you all very much.
And so before we move on to the reception out on the Chemistry Plaza, there is one more accolade that I would like to bring to Jeff's attention. But in order to do that, I need to call upon a very special guest. So please welcome Chancellor Carol Christ to the stage.
So good afternoon, everyone. I'm thrilled that all of you could come and enjoy this wonderful celebration in honor of Professor Jeffrey Romer. You've gathered together today not just to hear him deliver what I assume is an excellent Lewis lecture, though I just got the last 2 sentences of it, but to also award Professor Reiner with our university's highest honor, the Berkeley Citation. As it happens, he was selected for this singular recognition last spring, and well-informed sources tell me that the secret was kept in true Berkeley fashion, meaning our honoree is almost certainly in the know. Yet somehow any absence of surprise seems quite fitting, for I'm absolutely certain that word of Professor Reimer receiving the Berkeley Citation will come as no surprise whatsoever to his colleagues, students, friends, and family. The Berkeley Citation is awarded to distinguished individuals or organizations whose contributions to Berkeley go far beyond the call of duty and whose achievements exceed the standard of excellence in their field. It is an award that recognizes an essential truth about the essence of our university. All that Berkeley is, all that we stand for and represent, all that we are known and recognized for, flows from the people, past and present, who dedicate their professional lives to advancing our mission and our values. Rare indeed is the individual who better embodies all that we aspire and wish to be as individuals and as an institution in Jeffrey Romer. Professor Reimer's work has had a significant impact on chemical engineering. In addition to his advancements in research, he's an outstanding teacher and mentor and has provided exemplary service to the College of Chemistry and the Berkeley campus community for over 40 years. A review of his research finds a consistent, comprehensive focus on challenges and opportunities that run the gamut from the molecular scale to the existential expanse, all part of a compelling, multifaceted quest for new knowledge in service to and in support of environmental protection, human sustainability, and fundamental scientific insights. Professor Reimer is known for his dedication and devotion to preparing researchers to excel, not just in the lab, but also as leaders in industry, academia, and government. What animates him, what animates our university as a whole, a commitment to facilitating individual and institutional agency, the notion that through the discovery, dissemination, and development of knowledge, we can make the world a better place. Little wonder, then, that Professor Reimer's impact on the Berkeley chemical engineering community in regard to classroom teaching is as remarkable as the discoveries he's fostered and is reflected in the numerous teaching awards he's won at the department, the campus, and the professional level, including the UC Berkeley Distinguished Teaching Award in 2003. As one of his former students said, "I've never known any teachers who viewed teaching with such dedication to their students and with such devotion to the analysis and continual improvement of his own method of teaching." Throughout the years, Professor Reimer has been a highly effective fundraiser for the College of Chemistry. He's dedicated his time to cultivating relationships with donors, collaborating closely with college leadership on fundraising strategies, and making trips across the country to generate support for the college, among other activities. His outreach efforts have generated more than $20 million in donor funding for the Department of Chemical and Biomolecular Engineering alone. This is an extraordinary level of fundraising activity for a faculty member, and it's an example of how Professor Reimer's contributions to Berkeley have impacted the greater community and helped advance the mission of the College of Chemistry. Individually and institutionally, we've been enriched by Professor Jeffrey Reimer's presence and participation in our community. Congratulations, Jeffrey. This is a citation that cannot be more richly deserved.
Thank you. Setting number one.
Jeffrey's clapping. You're on the camera.
Thank you very much, Chancellor. Thank you so much. Yeah.
You can come back up here.
Thanks. I'm not sure I can say much else at this moment other than thanks to all, and a special thanks to exceptional leaders, Chancellor Christ and Doug Clark.
All right, now before you all leave, there is just one more celebratory icing on the cake. So, Maestro, strike up the band. Nothing gets the juices flowing like the cow band. With that, again, I'd like to thank our speaker, Jeff Reimer. Of course, I'd like to thank Chancellor Christ. And I also need to give a shout out to Clay Radke, whose idea it was to get the band. So credit where credit is due. So thank you all very much. Thank you. Please join us for our reception on the Chemistry Plaza. Thank you.